Okay, this week we will study further the complex analysis based on the Cauchy integral formula. So let's first recall what we learned last time. So this is Cauchy integral formula. And if omega is a bounded open subset with piecewise smooth boundary, and fz is a holomorphic function on some neighborhood U, or the topological closure omega bar, then we have fa equals 1 over 2 pi I line integral along the boundary of omega fz divided by z minus a dz for all a in omega. Okay, and the proof essentially just application of Cauchy theorem. And the Cauchy theorem, if in its smooth form, we can prove it by integration by parts or Green's theorem. But if you don't assume the smoothness of the partial derivatives of f, then you need to prove by contradiction. I will not recall the whole proofs, so if you forget, please go back to check previous lectures. Okay, next, as we promised before, that we had two definitions of holomorphicity. First one is given by the Cauchy-Riemann operator when you assume the holomorphic function f is smooth. Okay, and the second one is given by the existence of complex derivatives. For that one, you don't assume the partials of f are smooth functions. As we said before, they are essentially equivalent. So, remark two definitions. Holomorphic functions are equivalent. So how to prove that? We already know that if f is f satisfies Cauchy-Riemann equation, then we know that f prime exists. Okay, and also we show that all the power series is satisfies Cauchy-Riemann equations. So we have this direction. So next, very easily, we can show that. So this is the first definition. This is the second definition. So we will show that if the complex derivative exists, then f has a power series expansion locally. Therefore, you have this commutative diagram. First one and the second one, essentially, they are equivalent. Okay, so next we apply the Cauchy integral formula to show the following corollary. Suppose omega is an open disk with radius capital A centered at point A. With radius capital R centered at point A, and F is holomorphic on omega. So according to the second definition, then Fz equals Cn z minus a to n's power is a series of functions convergent on omega. Yeah, in mathematics, it's very important that when you say series, then you need to specify the convergent domain, because randomly you can just prescribe any constants, a complex number Cn here, but it's very to construct special sequence Cn such that the function doesn't make sense at some point. Okay, so you need to specify convergent radius. If you a little bit forget about this, then go back to Rudin's book. The corresponding section has provide some examples. For example, so if you consider this power series, then you will find nowhere convergent. Okay. So later on, when we carry out proof, we need to care about the convergent radius. Okay, so proof of the corollary is easy. We just apply the previous theorem of Cauchy integral formula. So take a smaller radius r less than capital R and apply Cauchy's integral formula to f on the following smaller closed disk. So if you draw a picture, why we need to shrink the radius a little bit is because in the theorem, you need to have an open set containing the closure of the domain omega. Okay, so here your original, suppose this is point A. Your original open disk is a radius R, but you cannot apply Cauchy's integral formula here. If you read the theorem carefully, what you can do is shrink the radius a little bit. As soon as it's strictly smaller than capital R, then you can apply the theorem on the blue part. Okay, so the theorem tells you Fz equals, so here Z is a point inside the blue disk, strictly. Okay, then you have the following formula. Okay, next, notice that because Z is inside the blue disk, then what do you have? Then you have Cauchy minus A, the absolute value is greater than Z minus A, or equivalently, Z minus A absolute value divided by Cauchy minus A is strictly less than 1. Hence, we can do the following expansion. So here you view Z as a variable. Viewing Z as a variable. Okay, see, it's in the denominator, but now you want to expand it as a power series. So the model type is, recall, 1 over 1 minus Z, which is given by this power series. Okay, then you need to do the following algebraic manipulation. Z minus A minus, Z minus A minus Z minus A, and you divide it by 1 over Cauchy minus A. You have 1 minus Z minus Cauchy minus A. Okay, if you look at this formula, it works only for absolute value Z less than 1. But here, because of the geometry here, we do have this condition. Therefore, you have the following expansion. Z minus A Cauchy minus A to nth power. And if you want to know the convergent domain, then it is convergent. It is a convergent power series for all Cauchy on the boundary of the blue disk and Z minus A less than R. Okay, now you plug in the Cauchy's integral formula. Then you have this one. Okay. Then we change the order of integration and summation. what do you have? You have, since the integration is with respect to Cauchy, so z minus a to nth power is a constant. So z minus a equals r f Cauchy z minus a to n plus 1th power d Cauchy z minus a to n. Sorry, this it's not absolute value. It's just parentheses z minus a to nth power. And here, for all z minus a less than r, this is true. And noted that this is a constant. Then we prove the corollary. Okay, so why we can change the order of integration and the summation? We make a remark. Is because we need to have some uniform condition. But as we promised before, or said before, the power series is uniform convergent in a smaller disk. So to be more precise, this is less than the supremum of f Cauchy. So Cauchy minus a less than or equal to r, and divided by Cauchy minus a to n plus 1th power times z minus a to nth power. Okay, since f is continuous in the green disk, then it's continuous in the blue disk, of course. But we have a theorem that on a compact set, a continuous function is bounded, has supremum. So this is a bounded number. Okay, and noticing that then we have, so let's denote this by I. So I is less than equal to supremum f Cauchy minus a less than equal to r, summation. So here Cauchy minus a just r. So times 1 over r. Okay, so this is a geometric series. Of course, this is less than party infinity. It's bounded by a constant. Then by the M test, the whole series so you want to specify this is what should I say? Yeah, anyhow, so this is uniformly convergent, has uniform convergence on C minus A equals R. Okay. Now here you view Z as a fixed constant such that Z minus A is less than or equal to R. Yeah, because the reason is as follows. Here, when we use the formula, in the proof, we view Z as a variable. But when you apply the formula here, interchange the order of operations here, you have integration with respect to Cauchy. So your variable should be Cauchy, and the uniform convergence should be on Cauchy. If you want to apply the theorem, how to change the integration and the summation. Okay, so if you forget about the theorem, so read Rudin's book. Okay, so the second thing is, which is also very important, is in the proof, you actually show that Fz is a power series with constant C and R. Because in your proof, you need to first choose a smaller radius R, and then everything here you calculate just this one. It's a constant depend on R from the proof. Okay, for Z minus A less than R. And so let's rewrite it. It's 1 over 2 pi I Cauchy minus A equals R F Cauchy minus A n plus 1 d Cauchy. Okay, but then for different radius R, probably you had different constant. Okay, so that is not so natural. Since in our mind, if you have power series expansion, then it should be unique. Okay, and then claim, in fact, C and R is independent of the choice of the radius small r. So how to show that? So I will leave it to you. So basically, so the idea is, if you have two choices of R1, R2, then the function f Cauchy minus a n plus 1 is holomorphic on z minus a greater than R1, less than or equal to R2. So in this annulus, the function is holomorphic. Apply Cauchy theorem. We derive this inequality. We derive Cn R1 equals Cn R2 for n from 1 to 3 all the way up to infinity. Okay, then actually what we have is Fz equals Cnz minus a to nth power. So here Cn just a complex number. And if you look at this carefully, then actually you can show this formula holds on the whole green disk, not only the blue one. But of course, it's not uniform on the whole green disk. It's uniform in any smaller disk and convergent on the whole green disk. Okay, so think about how to understand this formula. But anyhow, we showed that we established the first remark we made between the two definitions of holomorphic functions. So corollary applies this, then these two definitions are the same. In reality, when you want to check the holomorphicity of some function, a convenient way is to have some power series expansion. And later on, probably we will learn another, let's make remark 3. Another very important theorem, which says that if a fk is holomorphic and fk converges to f uniformly, then f is holomorphic. So this, you can see this is a more general theorem which compatible with the power series expansion. Okay, so in complex analysis, actually you have a lot of different ways to interpret the same thing, and each way has its advantage and disadvantage. So I want you to embed yourself into this subject and familiar with various interpretations, so that you are comfortable when you have real problems in physics, computer science, or whatever, mathematics, or whatever. So from my research experience, when you change the angle of view in some problems, the problem just is transparent as trivial. But if you still use the old point of view, then probably you will have hard time to understand some phenomena. So don't be bored. So ask why we introduce so many equivalent way to introduce the same thing. So I would say that's the purpose of this course. Just to get your life more complicated. You have a lot of choices. You are not just stick to some fixed definition. Okay, next, we want to generalize the Cauchy's formula to its derivatives. As we said last lecture, we want to show this. Of course, we need to specify the conditions, but I think as soon as you have this formula, you can guess what is a condition, what is a reasonable condition. Okay, so suppose U is an open neighborhood. Omega bar in C. And omega is a bounded domain with piecewise smooth boundary. And f is a holomorphic function. Assume f is a holomorphic function on U. Then for k equals 0, 1, 2, and all point z in omega, we have the integration formula for the derivative. So let's make a remark. When z equals a, actually this formula already known. From the proof of the previous corollary, we already know that. So just this formula. Okay, and so this is a little bit more complicated than the previous proof, but not that hard. If you're familiar with the proof of the original Cauchy's integration formula, then essentially the same. Okay, here we provide two proofs. So the first proof, on the first proof, we will expand everything in power series, and we know that to compare two things, especially in complex analysis, if you want to say two functions are the same, you only need to compare their power series and show that all the coefficients are the same. Okay, because of the uniqueness of the power series expansion. That's the idea. We expand everything in power series. So the first proof, compare power series. The second proof, if you look at the original Cauchy integral formula, where it is, oh here, oh yeah, this is not that good. Oh, but anyhow, if you take derivative with respect to a, then on the left-hand side you have derivatives or holomorphic functions. On the right-hand side, you do have fz over z minus a to a certain power. So the power depending on the how many derivatives you take. Okay, so that will coincide with the formula here. But of course, here you need to verify why we can take derivatives of the integrand. So the second proof, take derivatives of the original Cauchy's integral formula. Okay, so let's prove. So before we start the proof, we first reduce the theorem to a simpler case. That is, so we take a in omega such that Cauchy minus a less than r is contained in omega, and z minus a is less than r, less than capital R. So if you draw a picture, so this is probably your U. Okay. This is your U. And the blue one is omega. Okay. The shape of omega might be very complicated. It's not a regular disk or whatever. And Z is here. So what we do is we find a point A and a disk with radius capital R. Such that Z minus A is strictly contained in the disk. The reason why we do that is we want to change the domain to a little bit regular one, so then we can use the power series technique. Otherwise, in the whole domain omega, you cannot use power series expansion. Recall that what we proved in this query is actually what we show is locally holomorphic functions have power series expansion. We never say globally you have the power series expansion because it's not true. Okay. Then after we do this setup, then we can simplify the right hand side. So the right hand side integration equals, let's call this disk D. The integration on the boundary of D f Cauchy minus Z k plus 1 D Cauchy. Here implicitly we use the following fact: f Cauchy minus Z to k plus 1's power is holomorphic on which domain? On U subtract D. So here D, let's define D to be the open disk. Okay, let's call the variable Cauchy minus A less than R, or less than capital R. Okay, so basically you are using this. Okay, next we are going to prove that then it suffices to show that k is due to f equals to k factorial over 2 pi I integration along the boundary of the disk Cauchy minus A equals capital R f Cauchy divided by Cauchy minus Z k plus 1 D Cauchy. Now we use the power series technique. Look at the left-hand side. This part, let's do some analysis. So before we go on the left-hand side, we have power series expansion from the proof of the Cauchy. Therefore, on this side, we want to expand the integral as a power series. Okay, basically, we want to expand the rational function 1 over Cauchy minus Z to k plus 1's power. So recall we have the following formula. So here we use the property that Cauchy minus A equals the radius capital R and it's greater than Z minus A, norm of Z minus A. Later on when we do the Laurent expansion, we will meet such a case. You interchange the role of Cauchy and the Z. Then you have different version of power series expansion. Then how to do the power series expansion of this function. This is kind of some combinatorial technique. If you expand this and do product, of course you can view this as a product. Then one way is 1 over Cauchy minus z times 1 over Cauchy minus z, blah blah 1 over Cauchy minus z. You can do this, but then you have a product of infinite series. It's a little bit difficult to get the coefficients. Okay, so we will not. You can do that, but it's just more complicated. And so we have second interpretation. This is just d over dz. To k's power. So when you take k's derivative of 1 over Cauchy minus z. And of course, you have some power, you have some coefficients, 1 over k factorial. Okay. Then you can just plug in the power series here. Then apply it. You have 1 over k factorial integration n times n minus 1 times all the way n minus k plus 1 divided by Cauchy minus a n plus 1 z minus a n minus k. Okay, then look at the right hand side of the formula. Star, so right hand side you have k factorial 2 pi I integration Cauchy minus a equals r and f Cauchy times 1 over k factorial summation n from 0 to infinity n minus k plus 1 Cauchy minus a to the n plus 1's power z minus a to n minus k's power. Of course, the integration is with respect to Cauchy. Okay, then you see here we need to interchange the order of integration and the summation. So by the previous estimate about the uniform convergence of the integrand, we can do that. So in other words, we can compute this as here should be k. Because if you take derivative of constant, then you get nothing, just vanish. Okay, and here you have n times n minus 1, n minus k plus 1, z minus a, n minus k. Those are constant because the integration is with respect to Cauchy. And then Cauchy minus a norm equals r f Cauchy. Cauchy minus a n plus 1 d Cauchy. And probably you already noted that this part is a derivative of f k's derivative, n's derivative of f at point A, which is a coefficient of the power series. More precisely, Now let's look at the left-hand side. Left-hand side. What is the left-hand side? Case derivative. So d dz case derivative and the power series summation n from 0 to infinity. And what is the coefficient Cn? So the coefficient Cn is here. So this part 1 over 2 pi I. You just change 1 over 2 pi 1 over 2 pi I. You change z to a, so f cos z minus a equals cos z minus a equals capital R. Oh, just a typo here. It should be capital R. And f cos c minus a n plus 1's power d cos c. Okay, then you take case derivative. Oh, sorry. This is the coefficient, and z minus a to n's power. Okay, then you take the derivative. Here again, you use uniform convergence of the power series, or just use the property of the power series. You can take a derivative turn by turn. So I will say, think about why this is true and why this is true. I think most hard analysis part of this course is about uniform convergence, or do some estimate of the error. When we learn Fourier analysis, we will carry out those in full details. So if you are not that comfortable with interchangeable orders or operations, so don't worry. We do have time to practice. So just make yourself comfortable with the proof. So here we need to change the order. If you are comfortable with this change order, it's okay. Because I know some of you are physicists, some of you are computer scientists. So don't worry too much about the rigorous part at this moment. Okay, then here what do you have? You have you take a derivative of z, so here you have k factorial. K factorial and 2 pi I 2 pi I and integration blah blah plus 1 d cos c. This is a coefficient z minus a m minus k. Oh, sorry, it's not k factorial. It's n times n minus 1 times n minus k plus 1. And here I forget 1 over 2 pi I. Okay, then you compare these two terms. So we have left-hand side equals right-hand side. Oh, we are done. So this is first proof. So the reason I introduced the first proof is because I want you to familiar with some basic technique, the Taylor expansion, power series expansion. When we want to show something, two things are equivalent, probably one way is to expand them to some basis and then compare each of them, each coefficient of them. This is also a common technique in Fourier analysis or in the function analysis. When you want to compare two things, you just expand everything in some basis. Actually, the most basic, this idea comes from the most basic example as follows. Idea comes from comparing 2 points, for example, in Rn. So Rn, suppose you don't have any coordinates at this moment. How to compare 2 points? How do you know they are same? Probably you don't have a way to control it. And but normally we know how to compare them. We introduce a basis and write A equals A1 AN, B equals B1 BN. So A equals B if and only if A1 equals B1, AN equals BN. So that's the same idea. But of course, in reality, you do have some subtlety to overcome. For example, if a function is only smooth, then probably you know all the derivatives. It's not enough to conclude all the information of the original function. Okay. But in complex analysis, it's always true because of the uniqueness. So later on we will show that actually you can show this by yourself. Fg holomorphic functions and F is Cn. For simplicity, let's see. Cn, Zn, G is, for example, An, Zn. Then F equals G at each point if and only if Cn equals An for all the coefficients. So if you know, you take G to be F, then you know F has only one power series expansion. So corollary power series expansion of F of holomorphic functions of a holomorphic function is unique. Okay. We will discuss this more when we talk about zeros or holomorphic functions. Okay, now we introduce the second method. Second proof. So first, we recall the following lemma. It's a real analysis property, and we prove it just by the similar argument as before. Show that uniformity or the continuity guarantee the interchange of two operations. So lemma. Suppose you have some real numbers, and fx is a complex valued function. It's not necessary to be holomorphic, but just the function has two components. It's a vector valued. You have two components, real part and imagined part. The product alpha beta and gamma delta. So here function is on two variables, x and y. So x is between alpha and beta, y is between gamma and delta. And such that the partial derivative, partial f, partial x, or f with respect to the first coordinate x of R2 is continuous on alpha beta. Gamma delta. So it's not only continuous in x variable, but continuous jointly in x and y. So recall, what does that mean for a function continuous in some open set in R2? Okay. So let fx equals the integration of small fxy with respect to y from y equals c to d. Then since f is continuous, then you can take derivative with respect to, the small f is continuous, so capital F is differentiable with respect to x. Therefore, this exists, and moreover, it's continuous for x between alpha and beta, and moreover, you can compute its value explicitly by the following formula. So first remark, we would like to interpret this as interchange of two operations. So dx so the lemma claims that actually you have this formula. You just interchange the integration and the derivative. Here the integration is respect to y, the derivative is respect to x. If they are with respect to the same variable, then you just turn back to the original f. Or you cannot talk about that thing, because after you integrate with respect to y, you don't have y variables anymore. It's a constant function with respect to y. Okay, now let's prove it. So first, since partial f partial x is continuous on alpha beta cross gamma delta, and by Fubini's theorem, on interchanging the order of the two integrations in an iterated integral, we have the integration for x from a to c, and then you integrate y from c to d of partial f partial x equals the integral for y from c to d, and the integral for a from a to x from a to c partial f partial x xy dx dy. So look up Fubini's theorem in Rudin's book on Wikipedia. Basically, I think the general form, if you know real analysis, the general form for Fubini's theorem is as follows. If a function is absolutely integrable, then you can interchange the integration orders. And here, a c just 2 points in the domain of alpha and beta. Okay, now let's look at the right hand side. Look at this one. Actually, you can compute the right hand side pretty precisely, because the first integrand, the inside one, just give you, okay, so let's step by step. The inside one just give you the original function, small f, by Newton-Lebanese formula of fundamental theorem or calculus. Therefore, star gives you the following: partial f partial x xy dy dx equals y from c to d f c y dy minus f a y dy. Okay, then you take a derivative with respect to c. Then what do you have? On the left-hand side, you just by the Newton-Leibniz theorem, because this is continuous function of x. continuous on X, then by Newton-Lebanese theorem, you have the derivative. Okay, so let's derivative of left-hand side equals the derivative of right-hand side. But look at the second term here is independent of Cauchy variable. Therefore, when you take Cauchy derivative, it's 0. So here you only have the derivative of the first term. Okay, now here by the Newton-Lebanese fundamental theorem of calculus, you have f partial x and Cauchy y. Remember, you need to plug in Cauchy. Okay, and the dy. On the right-hand side, what do you have? You have y equal y from z to d partial f partial Cauchy y dy. Okay, since actually x and Cauchy are the same thing, so here you might change Cauchy to x. On the left-hand side, you have the integral of derivatives of f. On the right-hand side, oh, sorry. Oh, my bad. My bad. So the right-hand side, actually, you just keep it, but you need to realize the inside is f Cauchy. So after changing it to x, you have this is dx fx. So we are done. Okay, having this lemma, then we can give the second proof. So suppose U is an open neighborhood of omega bar, and where omega has smooth piecewise smooth boundary, and the f is holomorphic on U. Then notice that the derivative partial x f Cauchy minus z. Oh, here I should say Cauchy is a complex I should first write down the formula. Okay, this equals f Cauchy minus z square is continuous jointly in z in omega and Cauchy on the boundary of omega. And z, the complex variable z, can be written down as x and I, y. Therefore, x is just a real part of the variable z. It's irrelevant to the Cauchy variable. So when you take an x derivative, you just view f Cauchy as a constant. So you do have this formula. And then by the lemma above, we can take, then we have also the original Cauchy's formula. We have the x derivative of fz equals the integration partial x Cauchy minus z d Cauchy. Just the derivative pass through the integral formula, integral symbol, and then you compute it. F Cauchy minus z square d Cauchy. And since f is holomorphic, then we can transform the derivative or complex derivative to the real derivative as follows. Okay. Then you apply this formula, applying differentiation repeatedly. We are done. Of course, here we are a little bit sloppy. To apply the lemma, but you can do that because in the lemma you do have variable x and y, real variables x and y from some interval. But here for x, the real part of x, you do have the same thing as in the lemma. But then for the Cauchy part, okay, then you need to just view this as a line integral. Use parametrization, cut it into small pieces. Use line integrals to parameterize it. Otherwise, omega, the Cauchy part, the variable is curved. Okay. So I suggest you to work out the details. How we apply the lemma. Okay, I will stop here. Next time we will talk about some application of Cauchy's formula.